We are pleased to welcome Professor Pankaj Kumar Sharma from Assam University, Silchar. He will be presenting Introduction to Quantum Artificial Intelligence and Machine Learning. Professor Sharma is a distinguished computer scientist with a PhD, MTech, MSc, and BSc from the University of Delhi. His research areas include data mining, machine learning, optimization algorithms such as ant colony optimization, class imbalance learning, and bioinformatics. His work bridges theoretical computer science and practical solutions for complex data problems, including alert generation and association rule mining. Please join me in welcoming Professor Pankaj Kumar Sharma.
Thank you.
Over
Thank you and good evening,
Professor
everyone.
Sharma.
Thank you and good evening, everyone, on this session. And I'd like to uh, express my thankfulness to the organizers for allowing me to having a session in this workshop in this FDP. And what I have planned here in this session is an introductory lecture on quantum artificial intelligence and machine learning. And I hope by now, actually, I guess there are already discussions have been taking place at depth regarding various quantum computing concepts. So therefore, my approach this stage will be just a little bit of summarization about the contents related to quantum computing, and then moving over to the fundamentals of artificial intelligence as we have, with little bit of background, followed by what would be the kind of artificial intelligence in quantum computing domain necessary for the time to come. So a broad-based lecture that I have been planning at this stage, without going much deep into each of the algorithms. I have not taken up in algorithm level at this stage anything, keeping in mind that the subject is developing at this stage and it requires more introspection into the concept as well as the applications that is coming by. Just 1 minute.
Professor
Sir, you are not audible.
Professor Pankaj, please unmute yourself. Professor Pankaj, please unmute yourself.
Right. Fine. Fine. So, yeah, now I think it's fine. Hello.
Yes, but
Is it?
you have to share your screen again.
Is it all right now?
No, it's not visible. You have to present your slides.
Okay. Right.
Pankaj sir, you go
Huh?
to slide sharing, presenting your
Yeah,
screen again.
yeah, doing.
You're done.
And that's done. I think it's now okay. So, as I have mentioned that to summarize the quantum computing scenario, as you know, this has been based on the laws of classical physics as of now, though the working of the electronic components in the circuits, they follow the quantum mechanical principle. But the logic that is implemented on these circuits are classical in present day computing. Traditional computer software are also designed for serial computation. So in serial computation, as you know, in an algorithm, the logic flows from top down one point to another in terms of time. This means a particular process is to be completed before the start of another process. And this moves on till the end of the computation. At the same time, we also have the concept of parallel computation in present day computing within this traditional computing setup. Now, this parallel computation, what we now may call on classical computers or the traditional computers, is the concept of this is based on breaking up a problem into independent segments, independent logic and segments, and then this could be executed at the same time, and then putting them together in the end, that is integrating them, and then finally completing the entire computation. For example, simple matrix multiplication that we have, two matrices A, B are multiplied to produce another. Here, as you know, first element of C is taken and the first row of A is taken. First, to get the first element of C, the first row of A is taken and the first column of B is taken, and then these are multiplied to produce another, one after another, and then these are added. And secondly, to produce the next element, another row of the first matrix, second row, and the second column of B is used, and the next element of C, and like it goes on. And this process is parallelized, as the entire in case of big huge matrices, each of the multiplication components can be assigned to independent processors, and the elements will be produced independently, parallelly, that is what we call, and then they will be integrated into the final result. So this is traditional parallel computing, in which different computations are simultaneously done in different processors, and they are directed at the same time. But each processor on its own does not do any parallel computing, but it is at the algorithm stage, the logic is split into such parallel processes, and these are executed by different processors. Therefore, a traditional parallel computer can have many processors, and the job can be taken up at the same time, and then results are integrated. So therefore, independently computable functions are directed to process simultaneously by different processors. In contrast to this, a quantum computer exhibits inherent parallelism. I think this is already discussed, just to summarize. So this inherent parallelism goes into a little bit of history. Talked about how to simulate physics using computer by Feynman in 1982 in his paper Simulation in Physics on Using Computer, where he asked how to simulate physics on a computer, and the problem it got associated at that time was how to simulate time, first of all. But we are already familiar in this sense because we have been solving mathematical problems by simulating time by discretizing it and using differential equations and many other such things. So this problem could be tackled. But the next problem is that in quantum mechanics, the measurements give probabilistic results because we know the states of a in quantum mechanical state is a linear combination of certain other states, and when a measurement is done, suppose about some linear combination of some a linear combination of some basic states, and when a measurement of any physical property of the system is made in this way, so one of the possible values of that physical quantity is realized with certain probability. So this is a new concept in quantum mechanics, and it does not have a parallel in classical physics. Hence, this probabilistic aspect of quantum mechanics is one of the problems that has appeared. Now, moved on, use of quantum mechanics to build a computer. The problem now is that to simulate a quantum process using a quantum computer, can the quantum principle be used advantageously to eventually build a quantum computer so that it will start functioning with the advantage that we desire or we'd like to have in computing? Comes to source algorithm in 1994 for factorization of a large prime number in polynomial of log of time input size. This was a problem in classical computing because factorizing large number is recognized as a hard problem in computation, in computer science. That is intractable problem, in other words. So these intractable problems, which are also called NP-hard problems, does not have a solution in polynomial time. Its solution can be done only an approximate size of the problem in exponential time, or to some extent it can be, by downsizing the problem, can be brought down to the level of polynomial size solution. So this progress made by Peter Shor, in which used the principles of quantum mechanics and developed an algorithm to solve this old problem of computational science effectively with a quantum computer, that is the factorization of a large composite number. But yet this computation is not physically realized beyond a small number as on now. Only it is a theoretical possibility. The reason being, we do not have a machine of that size which can allow to compute a large number physically. So therefore, the factorizing a composite large number, it was an NP-hard problem, as you mentioned, and there is no effective algorithm which was known at that time or even now in classical realm of computer science to compute the factors of this composite number in polynomial time. The computation time, this polynomial time concept, is actually the algorithms in computer science or computational algorithms are analyzed what is called in terms of time complexity and space complexity, or in general, it is complexity of the algorithm, in which the computation time is expressed as a function of the input size. Now, such problems which are treated as intractable in computer science cannot be solved in polynomial time. And that's why these are not easy problems, these are hard problems. So factorization of this has been one of these. Now, such factorization is required in data encryption works and security aspects of many things as of now. So therefore, factorizing a large computer, a large, composite number would be definitely helping data encryption. And this, the algorithm in classical computer science for this was RSA algorithm, for which data encryption, it depends on the relative hardness of the factorization with respect to the multiplication, which is relatively easy. So RSA algorithm is the mainstay as of now. until Peter Shaw developed this theoretical possibility, and that was indeed a breakthrough. So therefore, breaking RSA code with Shor's algorithm, it is a theoretical possibility at this now, because we do not have a quantum computer of this size available as of now. So it leads to the advancement of cryptography and computer science. The second thing why quantum computation is different from classical computation is that, now talk about resistor. Like we have in our systems, we have electronic devices called resistors, logical devices. So now we'll be calling them as classical resistor because these are not quantum, cannot be. So these resistors of classical machines have to be in one on each state at a given point of time. That means for a 1-bit resistor, it can be, because we know it is either a 0 or a 1 state, so it can be either in 1 or 2 states. Similarly, if we have a 2-bit resistor, it can be in one of these 4 states at a given point of time: 0, 0, 1, 1, 1, 0, and 1, 1. Now the inherent parallelism that we spoke initially, how it comes into play in quantum computation. So this difference which the inherent parallelism brings is that between this classical resistor and the corresponding quantum mechanical statement, it is that in quantum mechanics, not only any of these four states can be stored in a resistor independently, but it can also be simultaneously existing as a linear combination of these 4 states. And when a function is computed, then one can compute the value of the function for this linear combination as well. Value of the linear combination as well. This means the value of the function can be computed for each of the input at the same time. And alternately, in quantum computer, this parallelism comes into play as an inherent property. Now, this parallelism, unlike in a classical computer, does not happen, because in classical computer, we are executing multiple processors simultaneously to bring the parallelism. Whereas in this case, this parallelism is happening within a resistor at the qubit level. So this leads to what is already discussed in the previous lecture, the entanglement property. In the entanglement property of the qubits. So just quick review of the entanglement, what we had. It requires minimum 2 qubit system for having entanglement, otherwise there will be none. And it does not have any parallel in classical computer. And then these 2 qubits on a particular state are not individually realizable. And if one of them is measured, the state of the other is automatically determined. So therefore, a quantum computer exhibits inherent parallelism. That is, the same processor can perform operations on multiple inputs simultaneously. In other words, the state of a resistor can exist in simultaneous superposition of different quantum states. Now, this is what a little bit of summary. Then coming to the need of such machine. As far as the computational science or computer science is concerned, why quantum computers are becoming a necessity or going to be a necessity in time to come. So it has the ability of solving the hard problems, but there are other reasons as well for this having this necessity. Speed of the classical computer have been increasing gradually. So one can argue as the speeds are increasing, so someday the speeds will be reached to a good level, so why? But increased speed of classical computers actually is accompanied with a great deal of what is called miniaturization in the integrated circuits. And according to the Moore's law, the number density of the transistors on an integrated circuit gets doubled in every 18 months to 2 years of time. This means the interspace or spacing between the transistors and the rest of the components are getting decreased consistently. So therefore, and this trend is going on, and as it is moving on, it leads to two major problems. One, as the separation of different components reach or may reach, if we move on like this, an atomic dimension, reach to atomic dimensions, then due to the uncertainty principle, if they come to so close, then the results of the computation will no longer be reliable because uncertainty will prevail. The second is the heat problem. The heat produced in the components will affect the performance. And again, the computation will become unreliable. So this is because at this level of dimension and with the increase of number of components, heat reduction will not be efficient. Why? Because heat produced by this computer depends on the volume occupied by the number of gates in the transistors, while the heat can be removed from the surface. Therefore, if the components come very close, the heat produced in one computer can damage or affect the functioning of the nearby component. So the next problem is about the reversibility. The classical computers are based on what is called irreversible process of computation involving mostly AND gates. Other gates are there as well. So this results in energy loss and leads to inefficiency with the increase in the number of components. So the quantum process has to be carried out reversibly to prevent the energy dissipation. So classical computing can also be done using reversible gates, but there is a garbage problem. The garbage arises because, for example, if an AND gate is used and if it is to be done reversibly, then it means that the inputs are to be continuously stored. And only NOT gate is irreversible among the classical gates. Therefore, if the computation has to be done with all other gates reversibly, the inputs are to be collected and these are not required later on. So therefore, disposal problem will arise and it will occupy unnecessary storage. Now comes the quantum advantage. Here, the advantage of reversibility is there. So every logical step can be reversed, resulting in negligible energy loss. And the garbage problem of classical reversible computation will not be here. So faster algorithms, we have the advantage of faster algorithms in quantum machines. We have to weigh out polynomial versus exponential time algorithms. The reason why it is important at this stage is because we are living in an age in which data holds the key to computing, and the volume of the data is increasing so high in an exponential rate that fastest of the machines are also not able to function in desired pace. So the requirement of high-performing systems are becoming a necessity instead of usable desktop or other such small devices. The second advantage is the database search of Grover's algorithm, which actually produced quadratic speedup. Of course, the source factorization algorithm is the other advantage, which is a major advancement in computing. And before this algorithm, the classical computer could not solve this problem of factorization. and the graph database search problem, which requires what was happening in Gover's algorithm is that it was of the order of n classical computation in case of Grover's search. But quantum database search, what Grover's algorithm performs is it takes unstructured database as an input and produce speed up, which is quadratically faster as compared to the classical model, which is therefore it requires only root n number of queries instead of n queries. And as we know, even data and database, there differences are there in many sense, because the database systems which you talked about till 20 or 15 or even 10 years ago were built on structured database systems like models. But today, the concept of data has actually totally overthrown the concept of structured database, because anything can be data, and everything of this sort is important for performing computation, because we have AI to be followed and the ML to be executed for high quality computing, high performing computing. Now, computational complexity is the other issue which talks about resources utilization. So computational problem is determined by the function of the length of the input in this case. So therefore, all these are the reasons why it has become a necessity to have a quantum machine. But then, as you know, in science as a whole, the concept goes faster as compared to the actual systems that is developed. So algorithm development has to take place prior to it is being realized in machines, or we do have machines for such computation. So therefore, coming over to the primary topic of quantum artificial intelligence of this session, once again, quantum AI is not going to my mind, bring up something new altogether. Quantum artificial intelligence will be just a new way of implementing the artificial intelligence that, as you know, or as we are facing or encountering, or as we are experiencing as of now. Then in quantum, first let's have a brief overview of AI. Here, what is AI, and how a quantum AI will be beneficial or rather required. And that is the objective of this session at this stage. So if we go back to the beginning, this term artificial intelligence was proposed in this paper, in this report, a proposal for Dartmouth Summer Research Project on Artificial Intelligence in August 1955. McCarthy, Minsky, and Rochester and Claude Shannon. They were one of those people who were part of this summer project, summer session, and then on it moved. But then artificial intelligence, then by intelligence we all are familiar what we know. Intelligence refers to ability to learn, understand, and think, as per Oxford Dictionary. Now, if we want to have artificially this intelligence is realized on a computing system, then what is to be done? Broadly, AI has to make the computers make or do or implement things which at present as human we do it much better. In other words, we want such skillful machines which should be in a way acting like human, or able to do, means it is the ultimate goal maybe, but able to do such tasks as human we do. Some examples I put it here is speech recognition. We do have speech recognition, a good technology, very sound technology available as of now. Smell, recognizing smell, recognition of face, objects. Intuition is now one of the areas in which lots of work is taking place. related to sentiment, intuition, drawing inference. And all this requires learning insights or learning new skills with a view to make decisions. And finally, abstracting the thinking ability, how these are made possible on machines. So at this stage, I'd like to refer many of the participants may know about. I followed the Norvig and Alan Rich book as a good text for artificial intelligence. As of now, the latest edition of Norvig is the fourth edition, and the Kevin Knight's book is on third edition now. So here they have grouped the actions of AI into 4 broad categories. An AI system, wherever we implement, should be able to think humanly. That is the benchmark or the goal setting. It should be able to think rationally. It should be able to act humanly and act rationally. So thinking goes first, action follows. So these are the broad situation. But the idea of artificial intelligence is not new, as we have just seen in case of 1955 report. But originally it was proposed by Alan Turing in computing machinery and intelligence, where a imitation game was proposed, where we have got in the downside on the right left corner here, we have an AI system hypothetically developed, a human conversing, and there is a human interrogator. So it's an imitation game. And now this is a setup which was a commonly called as Turing test setup. So this setup, if you see the bidirectional array set, this is continuously communicating each other to make it more perfection and to make the central communication channel is actually communicating with the system as well as a human, along with the imitation game human interrogator coming in from the other side. So this was a model provided at that time. Now, Turing in computing machinery and intelligence proposed this, and the idea was, can machines think? If it can think, then it should be able to behave intelligently. So that means this imitation game is an operational test for this intelligent behavior. Means it is continuously interacting and testing how good the computing is in terms of exhibiting intelligent behavior on grounds of ability to think, ability to act as a human being. Now, certain predictions that by 2000, once it is already past, that time a machine might have 30% chance of fooling a layman for 5 minutes, layperson for 5 minutes in an intelligent machine, but the human will still act as a superior. And therefore, it anticipated subsequently the next 50 years up till 2000, all major arguments were against AI. AI were not flourished, rather argued against for a long time, till the 2000, till the round of the millennium, till around the millennium. But then there are other constraints too, because if we look back again onto the technology side, we did not have HPC as we have today. We did not have multi-core processors as we had today, even in 2000. So therefore, all the contents that an intelligent system has to process, the technology, the hardware, the processors are not capable actually handling that. So therefore, though the subject has theoretically, conceptually, and algorithmically developed, and therefore this algorithm, conceptual and theoretical development of AI leads to the following components of AI. which the AI capability is built is that knowledge, reasoning, language understanding, learning, and of course there are more, but these are the four fundamental components, major components of AI. That knowledge, the system has to acquire and implement and use knowledge, perform reasoning actions, has to understand the language, and finally learn to execute or compute tasks. So therefore, coming to the four components, thinking humanly. So it is not content to have a program correctly solving it is not content to have a problem correctly solving a problem. So the system is not about, it is not enough to solve a problem correctly. It is more concerned with comparing its reasoning steps to traces of humans solving the same problem. When, as a human, we solve a problem, what are the reasoning steps we undertake? These steps also require to be simulated or understood by or implemented in the machine. And then, therefore, it requires theories to develop such capabilities and has an inclination towards the cognitive science domain. Broadly then, thinking rationally, that is laws of thought. Here we talk about formal logic mostly. So the logic theorist and formal logic, it provides a precise notation and rules for representing and reasoning with all kinds of things in the world. So irrefutable reasoning process, refutation, predicate calculus, first order, second order, all are part of this reasoning process. Then obstacle in this situation is informal knowledge represent. Knowledge can never be formal all the time, rather not. And secondly, how to represent this informal knowledge, because knowledge the system has to acquire, but when we want to store knowledge in certain forms, we have to store it in the hardware of the system. That means we need to have some kind of representation to be developed abstractly and then finally in an executable manner. Then coming to computational complexity and the resources at the hand. Coming to the next component, acting rationally to achieve the goals and based on the beliefs. So does not necessarily involve much thinking. So here the advantages in this component is that it is more general than the laws of thought approach and more amenable to scientific development than human-based approaches. So just a quick glimpse at this development, philosophy. These are the components of AI actually. It all involves philosophy, mathematics, helps in designing algorithm, computational, decidability and tractability, probability and all that. Tractability we have already discussed in this factorization issue. Then foundations of, then adaptation from psychological point of view. Then coming to knowledge representation, linguistics and grammar, all become part of the AI development. Now, again, looking back, the gestation of AI started in 1943. It moved on to 69. Then there are certain early successful implementations like checker game playing. It was mostly involved in game playing software development then. And then, logic theorist and geometry theory improver is another application. Then in that, as you mentioned, it has to, the arguments goes against, as the reason was basically not availability of systems. So the dose of reality it faced and the computational complexity is too high to be dealt. And then the neural network which emerged, and almost the research in neural network almost come to a halt because in such situation. Then some of the problems like Mycin, Prospector, and Dandrel, these are some of the early problems of knowledge-based systems developed in late 60s and 70s. Subsequently, the Mycin and other what are called expert systems. Subsequently, it became an industry around 80 because VLSI has become a reality, and we are getting by then high-speed machines. So naturally, the research in neural network and novel AI get a boost, and what we are seeing at the turn of the century or the millennium, what we have today. So based on this background, at present, these are some of the task domains of AI, doing mundane tasks involving perception, vision, and speech. In case of natural languages, understanding, speech generation, language generation, translation, and related all tasks. Then common sense reasoning, another class of work, which we human are extremely good. Robotics, robot control, games and all are informal tasks. Expert tasks are engineering tasks like design, fault finding, manufacturing, medical diagnosis, and many other such tasks in the health sciences, scientific analysis, and financial analysis. So these are some of the broad tasks that we are expecting to be transformed into quantum domain from the classical domain of AI. So in order to do that, what AI has, how the artificial intelligence development has addressed this problem. So first of all, recognize that AI, after these initial years or of exercises or research, one thing, these are some of the things which have emerged for AI to flourish. Intelligence requires knowledge. And unlike our number system, mathematics, algebra, the knowledge possesses less desirable properties, that these are voluminous, unstructured, maybe hard to characterize accurately, and it keeps on changing, and it differs from data which we are normally familiar with, and differs from, of course, mathematics, conventional one we do. So therefore, AI technique is what? It's a method that exploits knowledge, and that should be represented in such a way that knowledge captures the generalization. Means the knowledge acquired should be processed in such a way that one can develops the system, or one develops the ability to generalize the concept. And it can be understood by the people who must provide it. It can be easily modified for correction of errors, and it can be used in variety of situations. So this is one game playing example I think most of you may be familiar with, 2% to game 3. Like we have a 1 3x3 plate, array, or the matrix in the case. It's a two-dimensional scene. So here the idea is that game conditions will be filled, will be provided. Winning leads to +1, a draw is 0, and losing -1. This may be a condition that is put. So when game starts, there are 9 slots. The idea is to, the game condition may differ, but in this part of the figure, what we have is that the right diagonal, right to left diagonal, need to be filled in first. Whoever does it, he wins. So it goes on like that, and as you see in the end, the one below here, this diagonal is filled up, but other two hasn't filled up. Of course, multiple levels of the 3 has been omitted just for brevity to explain this. So this game playing, the idea is that in this game playing situation, there will be so many steps. Sorry. Each of the node at its level is leading to at most 9 branches, but once the branches are filled up, then the rest of the branches are to be searched. So therefore, computationally, it has becoming a problem of search. The player has to keep on searching the right move and the right option. So in other words, such game problem become combinatorially explosive. So These are some of the state-of-the-art situations as we have. We have got good computer games where human is beaten. Conversation using speech recognition is possible. Expert system we have now controlling spacecraft. These are the state-of-the-art as on happening now. Quickly move on. So these are some of the summarized definitions I have put in based on the developments of last 15 years since 1978 to 1993, where many proponents or many experts of this domain actually how they have viewed this subject has been broadly stated. According to Bellman in 78, the automation of activities that we associate with human thinking, such as decision making, problem solving, learning, etc., are part of the AI. Subsequently, Hoagland in 85 says it is exciting new effort to make computers think, that is machines with mind in full and literal senses. Sarnik and McDermott, who has a extraordinary text written on AI, they said study of mental faculties through the use of computational models. It goes on, and all these one thing can be seen that in all these statements about AI, different things have been mentioned by the authors, by the experts. So that means these are the things to be implemented. So subsequently, what it comes finally to a broad summarization, what is broadly recognized, such subjects cannot be defined as you all know. The study of how to make computers do things at which at the moment people are better by Rich and Knight in 1991. That is one of the most accepted view about AI by then. But then it has also down the around 30 years, 35 years since, things have been much improved, rather evolved. And it says it is a collection of algorithms that are computationally tractable. Tractability is always an issue with computational algorithms, which requires adequate approximations of intractability specified problems. An intractable problem has to be made tractable by providing adequate boundary conditions so that we cannot have the entire size can be taken for computation, but downsizing it is possible to certain extent. So then comes the ability to perceive, reason, and act into the domain of AI capabilities. So therefore, branch of computer science, some call it is concerned with automation of intelligent behavior, as we are seeing now or observing, and the enterprise of constructing a physical. Now here it says that constructing a physical symbol system. So physical symbol system is actually, we all work actually with symbol systems, like alphabet number system, all are in essence symbol systems. So here also AI, talks about Ginsburg in 1933. It requires a construction of a physical symbol system. So this is somewhat philosophical at the same time, and at the same time, reality also exists because it talks that it can reliably pass the Turing test. So I have summarized this around 15 such statements, which actually combined together provides the objective of artificial intelligence. And this why this history I have included in this is that in quantum artificial intelligence, this is not going to change. This is what is to be implemented, but through quantum computation. So that is the fundamental. So therefore, what we expect in quantum artificial intelligence, we are not expecting anything fundamental change here, anything which will go for a fundamental change, but rather it will have to have those things which will enhance the ability of the computational capability or enhance the computational capability for the algorithms. With better algorithms, it will be able to deal with the intractable problems and so on, and bringing the computational intelligence as close as possible to human intelligence. So therefore, in quantum computing, quantum artificial intelligence, what we expect, it is quantum computing by using the principle of quantum mechanics. It will potentially enable faster computation and more efficient problem solving. And therefore, we expect quantum algorithms for artificial intelligence will have significant potential to meet the contemporary challenges. And the contemporary challenges are basically computing classical intractable problems, solving classical intractable problems. And the intersection of quantum computing and artificial intelligence is what quantum AI we can say. So therefore, quantum AI is an emerging field, theoretically developing very fast. Experimentally, we have to wait maybe some more years to have reasonable size algorithms implemented on actual physical systems. It is expecting to offer possibilities for advancing both the technologies, leading to design and enhance machine learning algorithms and creating more powerful AI models. Yes, here suddenly came the terminology machine learning algorithms. In AI, machine learning is actually part of AI because learning is part of showing intelligent behavior. So without learning, nothing will happen actually. So it has been part of the AI and has been evolving as a sub-branch of AI and flourishing into a mainstream branch of studies as of now. So therefore, the existing machine learning algorithms will also require to be enhanced through these powerful AI models in quantum computing environment. Secondly, artificial intelligence can be used for error correction and control sequences. These are two benchmark problem in quantum computing as of now, error correction and control sequences to optimize quantum computers. I think occurrence of error and sequence control already studied, and so I'll not move into that. But these are the two problem areas where quantum artificial intelligence is likely to play a very significant role, and that will perhaps help developing quantum hardware apart from algorithms for computing. Now we are looking into a few situations. Is it AI plus QC, quantum computing, or QC plus AI? Means who is for whom, in a sense. I am trying to address things from both ends. Means how a quantum AI can enhance existing AI models, AI computing, artificial intelligence computing capabilities, and reverse. In this case, in the first sense, how classical AI or artificial intelligence as we have as of now be enhanced by quantum AI. Of course, by developing faster and more efficient AI models for improved learnings. So computational speed and reducing the time and space complexity is the permanent or rather prominent or primary goal for any computing solutions. Because of inherent parallelism that we have and capability of processing by being in multiple states simultaneously, quantum AI hopefully should be leading to faster and more efficient training models without forgetting previous knowledge. So without forgetting previous knowledge, that means the retention capability, which actually none of the, of course, it is part of learning at the same time, has to be more strengthened. Presently, this retention is happening in the learning models, like in machine learning, through feedback loops. We, of course, at present have different learning terminologies here as well, like reinforcement learning, trial and error technique, basically. At the same time, feedback. In neural networks, these are feedback systems. In neural network, these are mostly implemented. So these models are expected to be sufficiently improved because of this natural ability of simultaneous inherent parallelism. Now, data processing and enhanced data processing. It is a necessity because learning is based on computing on large volume of data. Large data volumes are possible to be computed with only when we have faster algorithms. So currently, as I mentioned, that the computing on large data volumes require high performance machines, and in spite of that, still faster computing is becoming a necessity. So therefore, and also the data sets are getting much complex. As you mentioned, we are not having databases only, rather it is data sets. So it is a combination of all kinds of databases, structured, unstructured, images, audio, video, text, combination of everything. All can be data. So therefore, quantum enhanced machine learning techniques for various AI applications in NLP, natural language processing, is the other avenue where it also going to come handy. Image processing, prediction systems, these are some of the present day computational domains where volumes of computation is required, or rather are required, but due to the limitations of the current scenario, the problems are to be handled at a reasonable size in terms of data. So expected to grow through the enhancement of, through the quantum AI. Contrary to that, how at the same time AI can enhance quantum computing. I do not know though how it can be happening, but these are in a sense possibilities as we have seen, and the works of course are in progress. Optimal control, like it is actually development of algorithms required. So control sequences at the qubit level, at the processor level of quantum machines. Optimal control of applying AI methods to optimize the control sequences needed to manipulate qubits on quantum processors. Because noise minimization is another requirement, so simply increasing the qubits is not improving the computational capability. Rather, there are other issues cropping up. Second is quantum error correction. So effective error correction techniques for building more and more stable quantum computers are required. Here AI can come possibly a much come possibly to much help. Then algorithm design. As you mentioned already, uh, there are intractable problems in classical domain of computing. So algorithm design is possible and rather happening in the sense for development of rather solving such problems which are intractable in classical computing domain. So applications of quantum AI, it's not that these applications are different from present day applications, but the issue here is, or situation here is that the ability to computing with large volumes of data. Classical machines again has got the limitations that it cannot deal with, huge volume of data. So drug discovery is one of the major research domain at present in computational science, simply because design of drug molecules is a time-consuming process. And finally, when it is going to be delivered to the society, to the stakeholders, it takes a very long time in physical laboratories. So the simulation, machine learning mechanisms, AI, all comes in handy in this drug discovery uh, domain, and also developing parallel fields in this. Where drug discovery is one of the component is called pharmacoinformatics. So drug design and discovery. So it is, and so quantum AI algorithms is expected to accelerate this drug discovery process by simulating molecular interactions and protein folding and many other such actions which are interior to this. So certain works which I was involved in recent times in this domain was related to one issue of blood-brain barrier permeability problem of molecules, in which like in CNS system, in certain occasion, some molecules, drugs requires to break or requires to go past the cell membrane, blood-brain CNS drugs, and certain molecules need not. Because if they pass the cell barrier, then cell membrane, then it will have harmful effect. Now, how to determine such molecules from a large number of such molecules uh, of medicines, drugs, which will ultimately have this property. So we actually involved in certain work with the machine learning algorithms we have implemented through deep learning as well as other machine learning machines, machine learning algorithms. And some results do come in, good one. And one thing which got learned from this is that this drug discovery problem, of course, we were limited to two-dimensional activity only, needs to be done at three dimension as well. So it needs much more than what could be done in present day situation. So material sciences, again, a design of new materials with specific properties. Cybersecurity is never going to be a die-out scenario. It is always going to be dynamic. So here, the computing capabilities of the quantum artificial intelligence will definitely going to be helpful, because as the algorithms will develop for a security mechanism, so will be the threats. So there has to be a superior scenario to mitigate the threats by developing such algorithms which can perform better than traditional encryption methods, as well as techniques. Financial modeling is the other area, and there are so many such areas. I have only collected a few here to give an overview of the quantum computing, rather quantum artificial intelligence applications for the time to come. Then comes a situation of quantum supremacy. Why it is so, or quantum advantage. So it is one of the goals of quantum computing, in which it is to be demonstrated that a programmable quantum computer can solve a problem which no classical computer can solve in any feasible amount of time. Theoretically, quantum supremacy is there, but then unless it is realized on through physical computing machines, till then, of course, it is going to be a much short of the goal. But it is more of a problem of engineering than the developing algorithm as on now. Therefore, expected that advancement in artificial intelligence will benefit from quantum computing. And then these algorithms will have a fundamental scaling laws. As these algorithms will have the fundamental scaling capability. That means uh, scaling down the time complexity to polynomial time from exponential time complexity. So some tasks in fundamental computation are also having this scaling advantage, and these are essential for artificial intelligence. So in a sense, what happens in this quantum AI will be indispensable for collecting training data that is presently inaccessible due to classical machines, because data acquisition now nobody right now data acquisition has to be done through instruments, sensors, satellites. So therefore, certain patterns not even got collected because of the limitations of the classical instruments, machines. Therefore, training also remains incomplete for for performing the quantum, performing the artificial intelligence actions. So quantum computing, quantum artificial intelligence, through such algorithms will be able to optimize such learning architectures, and therefore it will be able to model such systems where quantum effects are important. So like discovering new medicines and many such other tasks. So this is coming to the end of today's presentation with this. Here certain challenges I put together. Scaling quantum hardware is one of the major challenges. This is related to scaling up the number of qubits and reducing the error in computation. Secondly, algorithm development. The idea is to, or the goal is to leverage advantage over classical algorithms. Presently, classical algorithms are performing better because we do not have physical quantum systems of that level what is required. Then cross-disciplinary collaboration like quantum computing, AI, and related disciplines. So, and many more, of course. So this is where I'd like to uh, close today, and possibly in the next one we'll talk from here on specifically on machine learning concepts, and then on to quantum machine learning, and would like to see one or two uh, present day problems which are being attempted through quantum algorithms.
Thank you, Professor Sharma, for your valuable and insightful talk. Now, this is the session for question answer. If anyone have